Okay, so in the last two lectures, we covered the method of steepest descent and Newton's method. In this lecture, we will see a combination of the two, and that is why it is called hybrid method. So the name of the method is actually Levenberg-Marquardt method. So before going to the method itself, we make an observation. Just before this, we studied two methods and they have contrasting properties. Steepest descent method has very good global convergence property, but slow local convergence. On the other hand, Newton's method has very good local convergence property, which is very attractive. And you would think that all the time you will use Newton's method only because of that. But global convergence, it simply doesn't have. I mean, there is no guarantee that Newton's method as it is will converge at all. Forget about with what speed. The good result about local convergence just says that if started sufficiently close. But who would know where to start? That is a problem. So global convergence is actually a property which an algorithm must have. Local convergence, it will be nice if it has fast local convergence. Mediocre also will do. Okay. Now, but then the way these two have exactly opposite kinds of properties, it seems as if there is a large number of possible methods in between. And till now, we have studied one from this extreme and the other from that extreme. At this extreme, steepest descent method is greedy. It quickly tries to move along the direction in which right now at this point it seems the function is decreasing fastest, but that doesn't help much in the long run. In the long run, it is slow. On the other hand, Newton's method can see far, but sometimes it sees wrongly. Okay, so that is the contrast. So what are those possible methods in between, which are midway somewhere? Okay, and those have a collective name. The full spectrum of methods of this kind, okay, which use local information. Okay, so information only at the current iterate and the neighborhood. So the general name of that class of methods in which both steepest descent and Newton methods fall is the methods of deflected gradients. So the idea is that the direction of gradient is this, and in the negative direction of which we want to go, but then the direction can be deflected. You know that when a vector is multiplied by a matrix, the original vector is in this direction. After the mapping, the vector may be a little in a different direction. So that is deflection. So methods of deflected gradients. So all methods which can be expressed like this in their iteration formula, they can be classed together as methods of deflected gradients. And the commonality goes further. All these methods use local information. Okay. Later, we will study some advanced methods which use not only local information but history also. But that we will see later. So, in the class of methods of deflected gradients, if you put identity in the place of this matrix and then find out alpha k by line search, then it is the steepest descent iteration. Okay. If in the place of this matrix you put Hessian inverse and you put alpha equal to 1, then you get pure Newton's method. Then in this place, if you put Hessian plus some scalar multiple of identity matrix inverse, then you get, and then alpha you determine by line search, you get what we studied as modified Newton's method, the method to salvage Newton's method, to put some global convergence in it. Okay, so all these actually fall in this category. And now what we are going to do is that in this category, we will design a method which will move around the spectrum as it finds appropriate. Okay, and this is the hybrid method of Levenberg and Marquardt, the form of which is very much like modify Newton's method. That is, the search direction is found by solving this. But this gamma, which in the modify Newton method, we decided to have something which is safe, and for that the eigenvalue analysis was needed, that this Levenberg-Marquardt method avoids. Okay, rather than determining gamma based on the eigenvalue analysis, eigenstructure analysis, here in Levenberg-Marquardt method we tune gamma. Okay, that is, iteration to iteration we just keep it as a factor, and that factor is adjusted based on some sense. Okay, let us try to discover that sense. Just imagine if gamma is very, very small, then what does that mean? That means whether you are adding this term or not to the Hessian, it hardly matters. Okay, so Hessian is the one which will be sitting here, and this will be inconsequential. Okay. On the other hand, if you put a large value of gamma, that will mean what? This will be something, say, if you have put gamma equal to 1000, that means this is 1000 times the identity, and then whether this in these the eigenvalues are 34, 72, minus 3, minus 17, 1.5, how does it matter? Okay, so with 1000, whether you add 32 or whether you add 3.2 or whether you subtract 1.5, it doesn't matter much. Okay, so effectively this will turn out to be something like 1000 times identity. Okay, that is a scalar multiple of identity. As a result, the direction decay will be in the direction of negative gradient. Whatever may be then alpha, that's a different thing. That will depend upon this large number. So if this number is large, then decay magnitude will be very small. But if you are in the habit of normalizing the direction, then anyway all those directions will turn out to be the same thing, because the direction is anyway fixed. So it will become basically steepest descent method, right? So that means at one end of the spectrum with gamma very large, you get a preponderantly steepest descent kind of behavior. At the other end, with gamma very small, you have a dominant Newton kind of behavior. And that means with different values of gamma in between, you get whatever in between you want. Okay, and this is tuning. So we have this parameter gamma, which we tune through the iteration. How? Initially what? Finally what? Finally, that is towards the last iterations, you would have converged near the actual solution. And there it will display a nice quadratic structure for the local neighborhood, convex. Okay. And therefore, in that locality, Newton's method will be great. Right? So there you would need gamma to be small. On the other hand, when you are starting the iterations, at that time, you are likely to be very far away from the actual solution x star. X0 must be quite far away from x star. I mean, typically that is what you expect, right? So initially, you would like to favor steepest descent method. So to get the advantage of both sides, in the initial iterations, global convergence of steepest descent, and at the later iterations, when you are close to the minimum point, to take the advantage of the Newton's method, you tune from high to low. Okay, but not like continuously decreasing according to some factor. It's not that you start with 1000 and then go on half, 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 half. No, nothing like that. You can go on half, half if there is progress. On the other hand, if some iteration say doesn't work all right, then you can increase also. So in a typical run of Levenberg-Marquardt method, you would find that gamma from a very high value, if you keep on tracing that, from a very high value, gamma keeps on reducing by whatever factor you have mentioned. And then in between, in a few iterations, it again goes a little high. That means now the iterates have entered a zone where the continuous progress has been sort of blocked because there is some change of shape of the contours. Okay, so it has to readjust itself. So the gamma is accordingly readjusted. So that means you start operating at one end and then keep on coming on the other side. And whenever you find that things are going wrong, you again go back to the safe side. So one end is safe end, the other is fast end. And by tuning gamma, you travel along that. Okay. So this is the arrangement. You would select a tolerance value, epsilon, as usual. Initial value of the tuning parameter, high. And update factors, mu1 and mu2, both greater than 1. Typically, you can take mu1 to be 2 and mu2 to be 5. We'll see where they are used. Okay. Select the initial point, evaluate the function value, and start the iterations. Okay. In the iteration, what will be there? You evaluate the gradient, the Hessian, and then with that gamma value, construct this, put the negative gradient on this side, solve for the direction. After getting the direction, conduct a line search, determine alpha k. Right now, do not update the variable x. Right now, find out what is the function value at the proposed new point. If alpha k is the line search result, then the proposed new point is xk plus alpha k dk. Okay, that is xk plus 1 is supposed to be. Right now, don't update it. Evaluate the function there and find out the change in the function. The new value minus the old value. Okay. Now, if this change is extremely small, less than the tolerance that you have taken, that means you have converged. Okay. Initially, it may not happen, but for some value of k, it will happen. That is what is expected, right? So if it is too small, then stop. Otherwise, you will come down. And now, if it is not too small, that is within tolerance, then you check whether it is negative or positive. You could have checked earlier also. If it is negative, that means there is progress. So there is progress. So things are going fine. And that is how you expect, right? So, and in the normal expectation, in the regular expectation, your plan is to decrease the parameter slowly, gamma. So decrease it, gamma by mu1. Mu1 is something like 2, I said. Okay. You can make it 1.5, you can make it 2.5, doesn't matter much. You have to have a policy. Okay. And now there is progress, so you make the update. Okay. On the other hand, if delta f is positive, that means if you go to the proposed point, the function value will increase. You don't want to go to the proposed point, so you don't go. Rather, you say that this gamma, I think over the iterations has decreased too much. Now we are at a position where if we operate with this gamma, then we are getting a proposed point where the function value increases. We don't want it. Okay, so of course we are not updating x, but then we have to conduct the next iteration. So gamma value, this small, is not appropriate. We will increase it. Now increase it by a factor mu2. I am suggesting 5. You can take something else, 3, 4, 6, whatever, 3.2, whatever. Now at this point, you would ask, perhaps, why did not you take gamma mu1 and mu2 same? When it is going fine, gamma is halved. When it doesn't go fine, then double it. If the factor is the same, half and double, okay, then what happens is that you see, when I have to increase gamma, then I did not take this step, right? Okay, I did not take this step. So now I'm at the previous step only, but previous point came by a value of gamma, after which gamma was halved and we are in soup. Okay, so now if I again double gamma, then that current point itself will be the best. Okay, so don't need to do that. Okay, I mean, it is not necessary because grad has changed, Hessian has changed, and so on. But while increasing, while making it safe, it's not such a bad idea to make it safe with a bigger factor. Okay, so for that purpose, I typically take mu1 and mu2 a little different, mu2 higher. Okay, and now you increment k, that is next iteration. Next iteration again starts from here. So this is the plan of Levenberg-Marquardt method, hybrid method. Okay, so some comments. Compared to modified Newton's method, as we studied it, I said this because one of my thesis students is trying to improve modified Newton's method, okay, to make it as competitive and much simpler compared to the best possible methods. Now, Levenberg-Marquardt method relaxes the computational burden because eigenvalue analysis it doesn't have to do. Okay? The computation of Hessian is the only major computation now, which we don't like. Okay. Other than that, it's not a big deal. So because of this Hessian computation necessity, Levenberg-Marquardt method is not considered the best compared to some more advanced methods which we are yet to study. Okay. However, Levenberg-Marquardt method is a very valuable method and it has a special utility. It has a special utility in those problems where a good estimate, accurate estimate of the Hessian you can find a little cheaply. Okay, and for that, Levenberg-Marquardt method remains as the method, professional method. Okay, so in that kind of problems, what really is the kind of problem? Suppose you don't have a scalar function but a vector function in which there are many functions, h1, h2, h3 up to hn, many, large number. Okay. Now you want to have small values of all of these. Okay. Needless to mention that in order to decrease h2, you may have to tolerate some increase in h1 and so on. Okay. But you want overall good. Okay. This also not too high, that also not too high, that also not too high. Okay. So together you want to minimize quite a few things. Okay. Too many, quite a few. No, I mean not just quite a few, but I mean quite a lot of things. That is why to signify that I have written capital N. How to minimize the magnitudes of all the components together in some sense. Now the sense which is widely accepted as a good sense is a sum of their squares because you want to minimize their magnitudes, right? So minus 1.5 and plus 1.5 both are equally bad or say equally good if you consider that as small. So you say that I will construct a master function like this, which is the sum of the square of all of them. Okay. And we have put a half so that after differentiation, a factor 2, which will anyway come, that cancels it. So it is immaterial. So in this kind of problems, Levenberg-Marquardt method will have an advantage. We'll see. If this is the objective function, then what would be the gradient? What would be the Hessian? So gradient would be, see, the functions were half sigma hi square. So now sigma will be there anyway, and hi square has to be differentiated with respect to x. So first twice hi into grad hi. That twice cancels that half, hi into grad hi. And such things, this is a scalar, this is a vector. So this product, this scalar times vector, all such things are equal to 1, 2, 3, 4, 5, 6. Okay? They have to be added. And you can write it like this through sigma notation, or these columns, if you organize like these column vectors, if you organize in these columns, then here in one single column, you will have h1, h2, h3, h4, which is a vector h. So you can write in this sigma notation or this matrix vector notation. So this becomes a matrix with all these. This should be grad h1, this should be grad h2, and this should be grad h capital N. Okay. So all have come as I. They should be 1, 2, 3, 4, and so on. Okay. And this matrix actually turns out to be the transpose of the Jacobian, okay, of H with respect to X. So we can write J transpose H. And now if this is the Hessian, or this, whichever way you want to see, then what would be the, if this is the gradient, then what would be the Hessian? Its derivative. So its derivative will have one component in which this will be held as it is, this will be differentiated, and that part will come as grad H transpose, that is this. Okay. Summed up for all n plus another term which will be, in which this will be kept constant, this will be differentiated. That is the ordinary Hessian of hi itself. That is this small hi, the function itself, times the Hessian of it, summed up again. Okay. Now this one, this term from here, if you, I mean, you can construct fresh, or you can see from here. So here, from here, this term would come when you keep J transpose constant, okay, and differentiate this. There will be J transpose, and the derivative of this is actually J. Okay, that is the Jacobian. So it will be J transpose J. Okay, plus this is same. Now, in the typical situations where we get this kind of problems, there what happens is that this term typically dominates the entire thing in magnitude, and this turns out to be typically small in comparison, and therefore even if we throw out this term, this will alone represent the Hessian pretty well. Okay, so if we can do that, if we can approximate the Hessian with J transpose J, then we can see that in evaluating J, we needed only first derivatives. At this stage itself, we knew J. Okay, and these second derivatives, small n by small n, capital N of those matrices, we don't have to evaluate, and that is the advantage. So this kind of problems are the problems where a good estimate of the Hessian can be made cheaply. What is left out is not much. What are those problems in which such situations appear? Famous class of problems, least square problems. You know, in almost every field, sometimes you try to model an unknown function. Okay, the function is just y of theta, only a single variable theta, or there could be two, who knows. Okay, whatever it is, but then there are some parameters. Because the function is unknown, you do not have the clear-cut representation of the function, but you have the form of the function in which some parameters you don't know. So those parameters are actually organized in X. Fine. The form of the function you know, and therefore you can evaluate the derivative, etc. if you want. Derivative with respect to theta you will not need. Derivative with respect to x's you will need. Okay. So, and these x variables you want to determine. Once you determine them, you would know the function completely. Okay. So, in the preceding discussion, wherever we had h1x, h2x, etc., now we will put the errors. That is, we measure the value of y for different values of theta. That is theta1, y1, theta2, y2, theta3, y3. So now in this model, when we put theta1 and some values of x, then we get a value of y1, y, but that is not the value of y1. So the distance difference, the measured value, the difference of them is the error at theta I value. Okay. So error between these two, okay, is the ei for value theta I. This should be y subscript I, like this. Okay. So it should not be like this. So y subscript I, the ith value of y corresponding to theta I. Okay. So these errors, large number of such errors, 100 or 20 or 50. Okay. So all these errors, E1, E2, E3, E4, at values theta1, theta2, theta3, theta4, etc., they are put in the place of H1, H2, H3, H4 that we discussed just now. Okay. And then this entire problem falls in that category. Make note that here capital N must be greater than small n. That is, the number of data points should be larger. No, a capital N should be larger. Okay. The number of data points should be larger than the number of parameters to determine. Because if it is less, then all the parameters you will not be able to determine. If it is equal, then yes, in principle you can determine the parameters, but it will be very bad because you will have then no way to monitor and check the error. What error finally you get, you will not know, because 5 data points will fit 5 parameters perfectly. Okay. So you typically need the data points much larger than the number of things that you want to determine. So if there are 5 parameters to be determined, I would suggest that you should take at least 20 data points. Okay. Otherwise, your estimates, your final errors would not be proper. I mean, they will not be dependable. Okay. This is one kind of problems. This is called least square problems, where the sum of the squares of the errors at different points is minimized. Another kind of problems will be systems of equations. Say there are 5 nonlinear equations together you want to solve. So call one of them h1x equal to 0, the other one h2x equal to 0. And since your method is iterative, you will supply x and try to improve that. So when you supply x, h1, h2, h3, h4, they will not be 0. They will be 5, minus 2, 7, and so on. Now, over iterations, you want to change x such that h1, h2, h3, h4, all of them get reduced in magnitude. So what you want to minimize? You want to minimize h1 square plus h2 square plus h3 square, exactly the kind of thing that we discussed. Here, capital N will typically be equal to small n. Typically, I said, because in the well-posed problems involving nonlinear equations, you typically expect the same number of equations as the number of variables, not too many. If there are more, then actually you will end up doing least squares. Okay, because more equations you don't expect to get satisfied properly by a single set of variables values. Okay. Another kind of problems may look similar to these if formulated in a manner. There is a kind of problem called multi-objective optimization problem, where you want to minimize several objectives together, several objective functions together. Okay? And then basically, there are many other formulations which are typically better. But then one simple formulation is that if I want to minimize F1, F2, F3, all of them together, their magnitudes, then it would be nice to minimize this sum. And then it falls exactly in the category in which we are discussing things. But here, I mean, first of all, this is a very limited way of looking at multi-objective optimization. Sum of squares getting minimized doesn't typically fulfill the purpose of multi-objective optimization problem, but it fulfills the purpose in a limited sense. But even in that limited sense, in such problems, capital N, number of objective functions, is typically less compared to the number of variables. And if so, then this J transpose J, this part of the Hessian, will not be dominant enough, in the sense that in that case it will be n by n, small n by n, but its rank will be at most capital N. Okay. In this case, capital N is small. So for example, there are say 5 variables and only 2 objectives. Then though it is a 5 by 5 matrix, its rank will be only 2. That means 3 eigenvalues will be certainly 0. And if 3 eigenvalues are certainly 0, then in the directions of those eigenvectors corresponding to which the eigenvalues of this are 0, the original eigenvalue of the Hessian, the second order derivative part of the Hessian, will matter more. Okay. So if capital N is less than small n, then J transpose J will not be the dominant component. Something which we needed to say that this part is good enough as the Hessian. The second derivative part we don't need. So that will not be valid anymore. And that is why in this kind of problems, even though the problem looks similar in form, this Levenberg-Marquardt method may not be of great utility. Okay. Now, there is a version of Levenberg-Marquardt method without line search. And there, in the mixing, in the hybrid method, in the mix of Newton and Cauchy, Cauchy is actually slightly Newtonized in a sense, because for a very good reason. Let us see the reason. And to see the reason, we better see through an hypothetical example. Suppose we have some voltage quantity, which is dependent on 3 variables, and we want to minimize this. We want least voltage, lowest voltage. And the voltage depends on x1, x2, x3, in which x1 is an angular variable, angle variable, x2 is a length variable in centimeters, and x3 is a current. Okay. Now, when you evaluate grad f, then you basically evaluate del f by del x1, del f by del x2, del f by del x3. Del f by del x1 will be voltage by angle, the dimension of which is voltage only. Okay. So del f by del x1 will be voltage. Del f by del x2 will be voltage by length, which is electric field. And the third one will be voltage by current, which is electrical resistance. Okay. Now, in the ordinary steepest descent formula, you then have delta x is equal to minus alpha grad f. Now, delta x1 has to be proportional to del f by del x1. Here it is angle, here it is voltage. Okay. And proportionality constant is alpha. Delta x2, which is length, has to be proportional to an electric field. And the third one is current has to be proportional to a resistance. Okay. Current times resistance is voltage. Now here the current, change in current has to be proportional to a resistance quantity. And all these three disparate pairs of quantities have their proportionality through the same constant alpha, okay, operating on all three equations, all three scalar equations. And this gives an arbitrary scaling of delta x based on grad f. And that is why the line search becomes very important for still managing the numerical values. Okay. Now, if you open out the three scalar equations from here, delta xi equal to alpha times this, okay, and then modified that by multiplying here just with a scalar derivative, delta del 2f by del xi square, okay, only that scalar in each of the scalar equations multiply with only this, okay. So then what will happen? Delta del 2f by del xi square into delta xi. This would be in the dimension of del f by del xi, which is here on this side. And then alpha becomes dimensionless. And then you will say that alpha becomes dimensionless, and in some sense, this is taking an element of the second derivative. From the Hessian matrix, this is the corresponding diagonal component actually. Okay, the off diagonal components are del 2f by del xi del xj. This is the diagonal component. So the major component, diagonal component of the Hessian is incorporated, and the proportionality becomes physically relevant, and the line search is not that crucial anymore, because anyway in the Newton's method, pure Newton's method, line search was not there, right? So right direction would be fine. And now you see why right direction would be fine. You are unlikely to overstep, because in the, this is, we are discussing the Cauchy part of it, steepest descent part of it. In that you are unlikely to overstep because their gamma is large in initial iterations when the steepest descent part is dominant. If gamma is large, then the direction magnitude will turn out to be small. Okay, so you are unlikely to overstep. So that safety is anyway there. And you would reach the Newton zone much later, and it is Newton zone in which it is Newton's algorithm, Newton's method, which has this danger of overstepping. But here you are reaching the Newton's method operational zone much later when it is close to convergence, and therefore it will not go that bad. So for general kinds of functions, we cannot do this properly, because for a general function at some time, at some point, del 2f by del xi square may as well be 0. Okay, and that may be dangerous, or negative, which will also be dangerous. Okay, but in the case of the Hessian matrix constructed as J transpose J, it will become negative never. Okay, 0 also it can become only if a full column of the Jacobian is 0. That will happen very rarely. Okay, so, and for that you can keep a separate defense. So for J transpose J, the diagonal elements will be mostly positive. You put some matrix J in terms of numbers or symbols, and then try to construct this J transpose J, you will see it. Okay, that how it turns out to be typically positive. It will turn out to be a sum of squares. Okay. the diagonal element. So now, with that diagonal element included in the Cauchy part also, in the Newton part anyway, the full J transpose J is there. So the least square problem or equation solving problem, in that kind of problems, there is a special Levenberg-Marquardt algorithm which does not waste time in line search. Okay. You construct the error vector, you construct the master error function like this, and then go as usual. These steps are same as the earlier Levenberg-Marquardt method. Okay, these are same. Now here, this is the only difference. Earlier it was J transpose J plus diagonal times identity, and that was damaging the dimensionality. Now you are adding something to the diagonal element only, right? To this. So in the diagonal element, just add gamma times that. So essentially, the diagonal elements get multiplied with 1 plus gamma. Okay? Initially, gamma is high. So it will be something like 101, 51, 25, 26, 13 and a half, okay, and so on. Towards the end, gamma would be very small. So 1 plus gamma would be close to 1. Okay? So that is like doing nothing in the later parts. So later part, it will be preponderantly Newton. Okay. Now, the rest of it is same as the original Levenberg-Marquardt method. Okay. So this saves the cost of the line search. Okay. And it works more or less fine. So both versions of Levenberg-Marquardt method operate fine. So this turns out to be a little more efficient. Okay, so what are the points to note from this lecture? The Levenberg-Marquardt method combines steepest descent and Newton method to take advantage of both kinds, and it is particularly useful. Other methods, for other functions also, for other problems also, you can use it, but it will be costlier than what we come across next in the other methods. Okay, it is particularly suited for solving systems of nonlinear equations and nonlinear least square problems, where the Hessian can be estimated without actually evaluating second derivatives. Incidentally, very much like Levenberg-Marquardt method, there is another famous method called Dogleg method or Powell's hybrid method. Okay, so that uses more or less the same theory base as this method, but it uses a trust region strategy. Okay, so I told you several times that after this we will study some more advanced methods which do better than Levenberg-Marquardt for general problems. But before that, we take a little detour, a little digression to see two little topics. One is solution of nonlinear equations, and the other is least square problems. To study those problems in their own right, and also see how this hybrid method gets utilized in that in more detail, perhaps with some examples. Okay, so in the next lecture, we will take up systems of nonlinear equations. First, one single equation, and then systems. Okay, so at this point, we stop here.